Hi everyone, myself P. Praveena. I'm the Assistant Professor of Mathematics in Institute of Aeronautical Engineering College. Today I want to discuss about the definitions on Module 3. That Module 3 name is Functions of Single and Several Variables. Okay, in that basic concepts, functions, okay, function and continuity and differentiability. Okay, here three theorems are there. That three theorems are mean value theorems. Under that first one, Rolle's theorem. Before going through that, what about the statement of the function, the Rolle's theorem? Okay, what about the statement of the Rolle's theorem here? Let f of x be a function such that it is continuous in closed interval a comma b, and the second one, it is differentiable in open interval a comma b, and the third one, f of a is equal to f of b. Then there exists at least one point c in ab such that f dash of c is equal to 0. Here, what about the concept of the Rolle's theorem? Here we have to discuss with the function. Here f of x be a function, it is continuous in closed interval a comma b. Okay, before going through that explanation of the Rolle's theorem, here what about continuity? Continuity means limit x tends to a, f of x is equal to f of a. Okay, that means limit x tends to a plus f of x is equal to limit x tends to a minus f of x is equal to f of a. Okay, if that condition satisfied, then the given function at x is equal to a, then that function is a continuity. What about the formula for that? Limit x tends to a, f of x is equal to f of a. Or else if you are taken the left and right limits for that, for the same here, limit x tends to a plus f of x is equal to limit x tends to a minus f of x is equal to what? The given function with respect to the given value a. Okay, if the three are equal, then the function is continuous. Okay, that is the concept of the continuous. And what about the second one? It is differentiable in open interval a comma b. What about the definition of the integration? What about the differentiation definition? F dash of a is equal to limit x tends to a, f of x minus f of a by x minus a. This is the definition, basic definitions for the differentiable, where the condition that was satisfied, the particular value of a, the given function is differentiable. Okay, therefore here what about the condition for the Rolle's theorem? It is differentiable in open interval a comma b. Okay, these are the conditions, and from this from one of the property, every differentiable function is continuous. Every differentiable function is continuous, but every continuous function need not be the differentiable. That means if the function is differentiable means definitely that the given function is continuous. That is the one of the property for the differentiation. Every differentiable function is continuous. Okay, there from the Rolle's theorem, whatever the first condition, it is continuous in closed interval a comma b, and it is differentiable in open interval a comma b. And what about the third one? F of a is equal to f of b. Third one, f of a is equal to f of b. If the three conditions are satisfied, there exists at least one point c belongs to ab such that f dash of c is equal to 0. Then there exists at least one point c in ab such that f dash of c is equal to 0. This is the theorem statement of the Rolle's. Here mean value theorems are three. First one Rolle's theorem, next one Lagrange's, and the next one Cauchy's theorem. For that 3, if you are explaining for that 3 means if you know the concept of continuity and differentiability, then easily we can get the values of the Rolle's theorem problems. Okay, this is the statement of the Rolle's theorem. Next one, Lagrange's mean value theorem. Let f of x be a function such that it is continuous in closed interval a comma b and it is differentiable in a comma b. Okay, it is continuous in closed interval a comma b and it is differentiable in open interval a comma b. Then there exists at least one point c in ab such that f dash of c is equal to what? F of b minus f of a by b minus a. Okay, f dash of c, here the differentiation is equal to what? F of b minus f of a by b minus a. Okay, if the function is continuous, if it is differentiable, then the particular at least one point that c value is in between open interval a comma b such that f dash of c is equal to what? F of b minus f of a by b minus a. Already we discussed in the previous classes that geometrical interpretation for the Rolle's theorem and Lagrange's theorem. Now I am discussing only the definitions of that third unit. Okay, then Rolle's theorem over and the Lagrange's theorem and Cauchy's mean value theorem. If f of a comma b closed interval a comma b tends to r, g maps a comma b tends to r, then what about the first condition here for the Cauchy's mean value theorem? Here we are assuming two functions, that is f and g. Here f comma g are continuous on closed interval a comma b and the second one f comma g are differentiable on open interval a comma b. Okay, again the two conditions satisfied. And what about the third one for the Cauchy is g dash of x is not equal to 0. G dash of x is not equal to 0 for all x belongs to AB. Then there exists a point C belongs to AB such that f dash of C by g dash of c is equal to what? What about the formula for that? F of b minus f of a by g of b minus g of a. Once observe, what about the Cauchy's mean value theorem first conditions? F comma g are continuous and f comma g are differentiable. There the third condition is g dash of x not equal to 0. Here once observe, if the g dash of x is equal to 0 means for the formula here we get the infinite terms. So that here compulsory the third condition g dash of x is not equal to 0 for all x belongs to a comma b. Then there exists a point c belongs to ab such that f dash of c by g dash of c is equal to f of b minus f of a by g of b minus g of a. These are the three statements of the theorems. First one is Rolle's theorem, second one Cauchy's theorem and Lagrange's theorem, and third one is Cauchy's theorem. In the previous class we discussed the related problems also. Okay, and next one, functions of several variables. Under that first topic is partial differentiation. What is partial differentiation? The partial differential coefficients of f comma x comma y with respect to x is the ordinary differential coefficient of f comma x f of x comma y when y is regarded as a constant. It is written as dou f by dou x or dou f by dou x or dx suffix x of f. Thus, dou f by dou x is equal to here. What about the formula for the derivative? Limit h tends to 0, f of x plus h comma y minus f of x comma y by h. Again, the partial differential coefficient dou f by dou y of f comma x comma y with respect to y is the ordinary differential coefficient of f of x comma y when x is regarded as a constant. Thus, dou f by dou y is equal to limit k tends to 0. Here we have to take with respect to y differentiation. For that, limit k tends to 0, f of x comma y plus k minus f of x comma y by k. Similarly, if f is a function of the n variables, Okay, for that x1, x2 and so on xn. The partial differential coefficient of f with respect to x1 is the ordinary differential coefficient of f when all the variables except x1 are regarded as constants and is written as dou f by dou x1. Okay, and it is written as dou f by dou x1, and dou f by dou x and dou f by dou y are also denoted by fx and fy respectively. Okay, if the function is in n variables, okay, here how we are writing that formula dou f by dou x1, dou f by dou x2 and so on. Okay, similarly here we have to denote dou f by dou x as fx and dou f by dou y as fy. Therefore, the partial differential coefficients of fx and fy are fxx, fxy, fyx and fyy are dou square f by dou x square, dou square f by dou x dou y, and dou square f by dou y dou x, comma dou square f by dou y square respectively. Okay, here second order partial derivatives are dou square f by dou x square, dou square f by dou x dou y, dou square f by dou y dou x, comma dou square f by dou y square respectively. The partial differential coefficients, these are second order partial differential equations. It should be specially noted that dou square f by dou y dou x means dou by dou y of dou f by dou x, and dou square f by dou x dou y means, okay, how we are differentiating dou square f by dou y dou x? First of all, f is differentiated with respect to x, and after that differentiate with respect to y, and f is differentiated with respect to y, and after that differentiate with respect to x. Okay, the student will be able to convenience himself that in all ordinary cases, that is dou square f by dou by dou x is equal to dou square f by dou x dou y. Okay, these are the partial derivative definitions. Here, what about the first order derivatives? Dou f by dou x, comma dou f by dou y, and second order partial derivative dou square f by dou x square, comma dou square f by dou y square, comma dou square f by dou x dou y, and dou square f by dou y dou x. These are the partial derivatives. Okay, now, okay, this is the basic concept of the partial derivative. Under that, I am explaining maxima and minima for functions of a single variable. Okay, that is, to find the maxima and minima of the function f of x, we use the following procedure. Okay, for that, okay, first of all we have to find the single variable maxima and minima, means we have some rules or procedures. For that, what about the first one? Find f dash of x and equating with 0. Okay, find f dash of x and equating with 0. Solve the above equation, we get x naught x1 as a roots. Okay, here solve the above equations, we get x naught x1 as a roots. Then find f double dash of x. Then find f double dash of x. If f double dash of x is greater than 0, then f of x is minimum at x naught. If f double dash of x greater than 0, then f of x is minimum at x naught. If f double dash of x less than 0, then f of x is maximum at x naught. Similarly, we do this for other stationary points. Okay, how we are finding the single variable maxima and minima means, first of all we have to differentiate the given equation and equating with 0, and solve that equations, we get x naught and x1 as a roots. For that, after getting that f dash of x, we have to find f double dash of x, that means second derivative for the function. Okay, if that particular value of x naught, f double dash of x greater than 0 means their minimum exists. If the particular value of x naught, f double dash of x is less than 0 means their maximum exists. Continue this procedure for the other stationary points. Briefly, I'll explain with one example question for solving minima and maxima for the single variable. That is, find the maxima and minima of the function f of x is equal to x power 5 minus 3x power 4 plus 5. Okay, for that, what about f of x, the given function, we have to assume that as f of x. For that, what about f dash of x? The derivative of that x power 5 derivative is 5x power 4 minus 12x cube. For maxima or minima, we have to equate f dash of x is equal to 0. For that, we get, okay, two values of x. That is, one is x is equal to 0 and another one is x is equal to 12 by 5. Okay, these are the 2 points of x. Okay, and for that, after finding that f dash of x, then we can take the second derivative of that, that is f double dash of x. Okay, for that first derivative is 5x power 4 minus 12x cube. For that, we have to differentiate that, that is 20x cube minus 36x square. Okay, at x is 0. Now we have to substitute these two values in the f double dash of x. Okay, at x is 0. What about f double dash of x? That is 0. F double dash of 0 is equal to what? 20 into 0 cube minus 36 into 0 square. This is 0. Therefore, f double dash of x is 0. Therefore, f is neither maxima nor minima at x is equal to 0. For minima and maxima means what are the conditions? Once observe the definition. If f double dash of x greater than 0 means their minimum exists. F double dash of x less than 0 means their maximum exists. But here it is 0. Therefore, there neither maxima nor minima. And what about the next value of that? X is equal to 12 by 5. For that, substituting the given f double dash of x, there we have to substitute 20 into 12 by 5 whole cube minus 36 into 12 by 5. That is 144 into 48 minus 36 by 25. After solving this, we get directly 1728 by 25. Is it greater than 0 or less than 0? It is greater than 0. Therefore, f of x is minimum at what? X is equal to 12 by 5. Therefore, where the minimum value exists at x is equal to 12 by 5, therefore f dash of double dash of x is greater than 0. Therefore, minimum value is f of 12 by 5 is equal to, okay, that is okay, after getting the f double dash of x greater than 0, where that condition satisfied at x is equal to 12 by 5, we have to substitute the 12 by 5 in the given function f of x. That is the minimum value of the function. Okay, I'm substituting there, that is f of 12 by 5 is equal to, let us take this as the first equation. There we have to substitute, that is 12 by 5 whole power 5 minus 3 into 12 by 5 whole power 4 plus 5. Okay, for that, that answer is the required minimum value of the function. Okay, this is the condition for the minimum. That means for the given function where that minima exists at x is equal to 12 by 5, and if x is equal to 0, there neither maxima nor minima. Okay, for the same concept, you have to explain with the functions of several variables. Functions of several variables. That is two variables. Here I am using two variables. Now I am explaining the concept of maxima and minima for the functions of the two variables. Under that working rule, first of all, same as the last concept, but here we have to use two variables. For that, what about the first one? First of all, we have to find out the given function dou f by dou x. That means differentiation of f with respect to x and differentiation of f with respect to y, and equating with 0. Solve these equations for x and y. We get the pair values of a1 b1, a2 b2, comma a3 b3. Okay, these are the stationary points. For that, next one, after getting the stationary point, again differentiate second derivative for the function, that is L is equal to dou square f by dou x square, and m is equal to dou square f by dou x dou y, and n is equal to dou square f by dou y square. After getting that second derivative with respect to x and with respect to y, and with respect to x and y, we have to assume that as L, m and n. L, M and N. Okay. For that, after getting that Lmn, now if Ln minus m square greater than 0 and L less than 0 at a1 b1, where you get that a1 b1? These are the stationary points after solving dou f by dou x equation and dou f by dou y equation. We have to substitute each and every stationary point in Ln minus m square. Okay, and L less than 0. If Ln minus m square greater than 0 and L less than 0 at a1 b1, then f of x comma y is maximum at a1 b1. A1 b1, and maximum value is, after getting that condition, for the particular value of a1 b1, the two conditions satisfied, their maximum value exists. We have to substitute the maximum value in the given function, that is f of a1 b1. Okay, similarly, and the next substitute the next point of that is if ln minus m square greater than 0 and L greater than 0 at a1 b1, then f of x comma y is minimum at a1 b1, and minimum value of a is f of a1 b1. For example, if the first condition is not satisfied for the particular value of a1 b1, that means maybe that condition satisfied at ln minus m square greater than 0 and L greater than 0 for the particular value of a1 b1, their minima exist. Okay, we have to substitute that minimum value in the minimum, that stationary point in the given function. There we get that minimum value. Okay, for example, if the two conditions not satisfied for the particular stationary point a1 b1, so that, okay, we have to substitute. That means maybe that points satisfies ln minus m square less than 0 at a1 b1, then f of x comma y is neither maxima nor minima. Okay, maybe the condition ln minus m square less than 0 condition satisfied at a1 b1, that means what? There is neither maxima nor minima. In this case, we have to a1 b1 is called as saddle point. Okay, you have to consider that a1 b1 as a saddle point. Third one, if ln minus m square is equal to 0 at a1 b1, no conclusion can be drawn about maximum or minimum and needs further investigation. Okay, for that, if we have to, that means whatever the fourth condition here, fourth means their third, that is if ln minus m square value is equal to 0 for the particular value of a1 b1, there is no conclusion. Therefore, that means what? No conclusion can be drawn about maximum or minimum. Therefore, we have to need the further investigation. Okay, similarly, we do this for our other stationary points. Here, how many we get the stationary point? We have to substitute each and every point on the condition of ln minus m square. Okay, if ln minus m square greater than 0 and L less than 0 means their maxima exists. If ln minus m square greater than 0 and L greater than 0 means their minima exist. And the third one, if ln minus m square less than 0, that means they are neither maxima nor minima. And the last condition, if ln minus m square is equal to 0, no conclusion can be drawn about maxima or minima. These are the conditions for the functions of two variables for finding maxima and minima. Next, okay, maxima and minima alternative method. This is Lagrange's method. Okay, that is what? Okay, this is alternative method for finding the functions of two variables for maxima and minima. For that, suppose f of x comma y comma z is equal to 0 and pi of x comma y comma z is equal to 0. We have to assume one as function and one as the condition. Okay, for that we have to take the Lagrange's function capital F of x y z is equal to small f of x y z plus lambda into pi of x y z, where lambda is called here Lagrange's constant. Okay, this is the condition for the Lagrange's function. Okay, for that after writing the Lagrange's condition, if now we have to differentiate capital F with respect to x and equating with the 0, that is dou f by dou x. Okay, that is dou capital F by dou x is equal to what? Dou small f by dou x plus lambda into dou pi by dou x and equating with the 0. Let us take this as the second equation, and from the first two are the 1 and 2 equations. And similarly differentiate capital F with respect to y, okay, and that is what dou f by dou y plus lambda into dou pi by dou y is equal to 0. Take that as the fourth equation. Similarly for the same function differentiate with respect to z and equating with 0, that is dou f by dou z plus lambda into dou pi by dou z is equal to 0. After getting the three equation, solve that 3 4 5. From that we get the stationary points of xyz. We get the stationary points of xyz. Substitute the value of xyz in equation 1. What about the equation 1? That is the given function f of xyz. Okay, we get the extreme value. Extreme value means either maxima or minima. Okay, this is the concept of the Lagrange's method of multipliers. This is the alternative method for the previous one. Okay, which one is, you can follow that. These are the basic concepts of the module 3. Okay, but what we discussed now, okay, all basic concepts of continuity, differentiability, and the related main value theorems, that is Rolle's, Lagrange's, Cauchy's, and partial differentiation, and after that maximum minimum of functions of one variable, and after that maximum minimum of the functions of the two variables. Okay, next class we will discuss with the other related definition from the next unit. Thank you for all.
Like, share, and subscribe. Hit the bell icon for more updates.